Hello, everyone. Okay, I think I'm live. I'm not sure if I'm mic'd, though. Okay, I think I'm mic'd now. Excuse my wardrobe. I literally rolled out of bed. So if you cannot hear me, please tweet it right away. I've got several computers open, and I'm looking at my Twitter feed now. Again, my Twitter handle is dionandan. I'm going to turn on my Google Hangout toolbox. Hang on for a second. And this will allow me to add a little more detail. Okay, let's turn on, and I'll add my Twitter handle so it'll be visible. Okay. There it is. So now you should see my Twitter handle at the bottom of the screen. All right, so I see I've got one viewer on Google+, which probably means about 5 or 6 on YouTube. Once again, how was yesterday? I assume you all survived. A little bit of excitement, it's not a bad thing. I actually went to class. I actually was there at 1 o'clock, just in case anyone showed up. And what I found was our classroom was occupied by the previous law class, all huddled in terror in the dark for God knows how long. So I just went home. Oh, 11 viewers now. Excellent. All right, so hopefully I wasn't too traumatizing for you. And we can continue on with today's review session. The review session really isn't needed because I'm just going to go over what we covered so far in this semester, and I'll talk a little bit about the midterm, but the slides are already online, so it's all there for the taking. So if you got any specific questions, email them to me right away, and I'm going to try again to share my screen and to see if I can get the Google Slides open. So once again, if the slides are not progressing, please tweet me right away. So I'm sharing the screen now. Here we go. Again, my Twitter handle is dionandan. So sharing screen now. I'm going to share. Hang on, what am I sharing? Let's cancel that for a second. Let's make sure I've got my oh, I know what I'm doing. I'm sharing this. There it is. I want that to share. Okay, so let's go back to my Google Hives, and I'm going to share this screen. Right. I'm going to quickly go semester, so let's begin. The midterm, first of all, is on Friday. We all know that. It's tomorrow. So today we're going to go over what we've learned so far and describe the midterm. The only formula I will give you on the midterm are these two here. So the two t-test formulas, one for the dependent samples and one for the one sample. I will also say that I've been looking at this textbook very carefully the last few days. This formula is from the textbook, and I think it might be wrong. It doesn't really correspond that well to a lot of the online calculators. Don't worry about that. You just stick to this formula, and this is what will appear on the exam if indeed this question is on the exam, and that's all you need to know. But do keep in mind, one of the reasons you may get different answers from online calculators is that I think the textbook might be wrong. So I've got to do a little more investigation right now. But don't put that out of your mind right now. Just focus on this formula here and stick to it, the same example we've done in class. So I'll also give you the relevant Z and T tables if indeed they are required. So if you need them to answer the question, they'll be there. Otherwise, you should be studying the other things like the relative risk formulas and things like that. Those you are responsible for yourself. There's no other materials brought in except for a calculator and a cup of coffee, if need be. So on lecture 1, if you recall, we talked about continuous variables and discrete variables. We went through the levels of measurement that define different kinds of variables: nominal, ordinal, interval, and ratio. And I think we spent a lot of time on that, so you know what those things mean, I assume. That's a quick summary here on the characteristics of those measurement levels. And we talked briefly about sampling. So with sampling, what we care about is the extent to which the sample that we are examining is reflective or representative of the larger population that we are referring to, called the population or the reference population. So that word representativeness comes up a few times. So if I'm sampling this class as an example of the entire university, how representative is this class of the entire university? And that brought us to talking about descriptive statistics versus inferential statistics. So descriptive statistics summarize the sample. So what is it about the sample that we can measure? Its average height, its average age, its average mark. As opposed to inferential statistics, which attempts to make conclusions about that larger reference population. And these are based on the laws of probability. How probable is it that what I've computed in my sample is representative of the larger population? And that brought us to talking about a parameter versus a statistic. A statistic is a characteristic of the sample, and a parameter is the corresponding characteristic of the population. So the mean age in my sample versus the mean age in my larger population. The statistic is very often used to estimate the parameter. In the second lecture, we talked about research questions, and defining independent versus dependent variables. The independent variable is free to be what it wants. The dependent variable depends on the independent variable. And the classic example here is smoking. Whether or not you smoke, you're independent. You can choose whether or not to smoke. Whether or not you get lung cancer is at least partly determined on whether or not you smoke. So smoking is the independent variable, and lung cancer rates are the dependent variable. Then we talked about how to define a variable. We said that there are two phases, the conceptual phase and the operational phase. So the conceptual phase was when we think about the thing that we want to represent or measure, kind of like how long you've been walking the earth. The operationalization of that idea is the variable, defining the variable. So your age in years is meant to represent the idea or the concept of how long you've been walking the earth. So in other words, the conceptual definition is the theoretical underpinning, and the operational definition of the thing that we can actually measure. Then we skipped over into frequency distributions, which is the heart, I think, of much of the second year class. A frequency distribution is the way that we arrange our data in our sample. In other words, how many times certain observations occur. How many rank that observation, sometimes as a graph, very often as a table, right? So the way that you construct your distribution is you list each of the data variables in sequence, depending upon how often they occur, and you add them all up. So we talked about relative frequencies versus cumulative frequencies. So the absolute numbers are how many cases there are. The relative frequencies is the percent of cases that those represent. And the cumulative frequencies is, as we move along the order, how many we have added on to how many you had previously. So here's an example. We have age here. So between those 0 to 25, there are 4 people that constitute 40% of our sample, and so forth. I'm skipping over this fast because this stuff is pretty basic. Right? We talked about the visual depictions of frequency, histograms, bar graphs, pie charts, and this thing called a frequency polygon, which is just an outline shape of one of these bar graphs. Here's a frequency polygon, right? So notice that the characteristics here is that the peak is a point, not a flat line, like a bar graph would be, and it goes down to 0. And we talked about probably the new stuff you hadn't heard before, and that is the shapes of distributions. Excuse me as I have a sip of my beverage here. Yummy. Right? We talked about modality, symmetry, and kurtosis. Let me just check my Twitter feed to make sure no one's contacting me. No one's contacting me. That's good. So if you remember, modality is essentially the number of humps there are. It comes from our term mode, which we'll talk about in a second, the most frequent elements in our distribution. So a unimodal curve has 1 hump, a bimodal curve has 2 humps, and so forth. Symmetry is about skewness, so how symmetrical our curve is around that center point, or that center mean average vertical line. So a positively skewed distribution has its hump to the left, actually. But its tail trails off to the right. It's a bit counterintuitive. A negative skew has its hump to the right and its tail off to the left. So do remember that it's the direction of the tail that defines the definition of the skewness. Positive skew, tail to the right. Negative skew, tail to the left. And here are two examples of that. We talked about kurtosis, which is probably a new concept for many of you. So kurtosis is the flatness or the peakedness of a curve. And there are three levels of kurtosis. There's leptokurtic, which is the thin, skinny curve. The platykurtic is flat, plat meaning plate, or that's where the platypus gets its name from, the flat tail of the platypus. So the more flat it is, the more platykurtic it is. And mesokurtic, which is something in the middle. And much like skewness, we have an index of kurtosis. We didn't actually measure that index, but I mentioned what it was and how to interpret the numbers. Here are some examples. A leptokurtic peak is skinny, and a platykurtic peak is flat. Then we moved on to measurements of central tendency, of the mode, of the median, and the mean. You know what these things are already. A mode is the most common measurement. Median is the central measurement, once you rank them all, and the mean is the average. We looked at measurements of variability, which is essentially the width of our distribution. The range is the obvious one, the highest value minus the last value. Interquartile range, I gave you a formula for computing that. And from the interquartile range, we defined our outliers. Remember, we have mild and extreme outliers. The mild outliers were defined as those 1.5 to 3 IQRs away from either end, and the extreme outliers were more than 3 IQRs away. We looked at standard deviation and variance. We have formulas for that. Here again are my definitions of outliers. Your data assignment number 1 incorporates some of this, so hopefully you're all experts on outlier identification now. We looked at the standard deviation, which becomes the heart of many of our tests that we do later, right? So a deviation is the difference between each measurement and the mean. The standard deviation is the average distance between each score and the mean. Okay, so depending upon which measurement scale you're using, that tells us which measurement of central tendency is most appropriate and which measurement of width or variability is also most appropriate. For a nominal scale, we can't compute averages, like what's the average place you were born. We can compute mode. So how often are people born here? And there's no measurement of width. For an ordinal measurement, like a ranking, we can't compute an average again, but we can compute a median and we can compute a range. But for interval and ratio measurements, we can do everything, which is why we love those measurements the most. So then we looked at how to look at the distribution, and we started to inch towards the normal distribution, computing standard deviations and so forth. We looked at variance, which is the square of a standard deviation. We didn't do a lot of time with variance, but we did note that it's important later on for some of the more complex or involved statistical tests we would do later. And we looked at notation. So the capital sigma is the parameter of standard deviation. The lowercase s is the statistic of standard deviation. And of course, sigma squared is the variance, and small s squared is also the variance in the sample. Then we looked at relative standing. So essentially, how you're doing relative to everybody else in that sample. How are you doing in this class versus how are you doing in another class? We looked at two things there, percentile ranks and standard scores. So standard scores are also z-scores or z-statistics or z-values, are also called normal scores. And it's the number of standard deviations away from mean you happen to be. That's all it is, right? And that's our formula. So to do a standard score, you need to know the mean and you need to know the standard deviation. Otherwise, you can't know how far away you are from that mean in terms of standard deviations. Okay, so we did that already. Cover that already. And this is our first experience with looking things up in tables, which is what the z-score was. Right, so we looked up our degrees of freedom and we find out what the z-score was and determined how likely it was that you are this number of standard deviations away from the mean. Okay. And then we talked about our 3 sigma rule. So if you're 1 standard deviation away from the mean symmetrically, that accounts for about 70% of the distribution. 2 standard deviations is about 95%, and 3 standard deviations is about 99.7%, almost all of them. Then we moved on to probability, which is probably everyone's least favorite lecture because it brought back conniptions and horrible memories from grade school. So remember that probability of anything happening is a number of possible successes of that thing happening divided by the total number of opportunities of it happening. We talked about the Boolean operators, or, and not. Or and are confusing. If something or something else can happen, it's actually more likely to happen, whereas if something and something else is happening, it's less likely. I'm constraining opportunity. So the operators that go along with these Boolean operators, with or, we're talking about adding, and with and, we're talking about multiplying, and not, of course, is subtracting. Then we look very briefly at some kinds of observational research designs, specifically cohort studies and case control studies. A cohort study looks forward in time. A case control study looks backwards in time. More precisely, a cohort study begins by defining or ascertaining our population's exposure status first, and a case control ascertains the population's outcome status first. So here's an example. For the question of, is taking antiretroviral drugs associated with developing nausea? Well, here's my study design. I find some nauseous people and some non-nauseous people, and I look to see if any of them took these drugs in the past. Right? So what kind of design is that? Well, what did I ascertain first? I ascertained the nausea first. That's an outcome. When I ascertain the outcome first, that's a case control study. So this is a case control study. Then we looked at making 2x2 contingency tables. It's critical that you set these up correctly, otherwise the formulas won't work. So the way that a 2x2 contingency table works is, on the left side, the exposure goes in that order. The exposure you're looking at is first, and the unexposed is second. And on the vertical distribution here, the outcome goes. And the outcome you're looking at goes first, and and those who didn't get the outcome goes second. And you fill in the cases appropriately. All right? And from the 2x2 tables, we developed a series of indicators, computations, measurements of risk specifically. We have the absolute risk reduction, we have the relative risk, we have the relative risk reduction, and we have odds ratio. We also have the number needed to treat. So we did a lot of exercises of those things. Just go over those and be comfortable with doing the calculations. I don't give you the formulas for this in this exam, so make sure you know these. The odds ratio, the fast way, is just A times D divided by B times C. So the cross product quotient, we call that. Then we looked at correlation. Correlation is a connection between two variables, usually two continuous variables, in a way that usually shows a linear kind of relationship, but not always. It can be something called monotonic. As one changes, the other one changes with it. Or as one changes, the other one changes in the opposite direction. Either way, there's a connection there. So I won't expect you to know this table of how to interpret experiments are. Don't memorize this. There's no need for it. Anything like this, if I require you to use this, I will put this on the exam sheet, so don't worry about it. But just for your knowledge, this is how we interpret the qualities of a Spearman's row, or a Spearman's R, Greek letter rho. Okay, so remember that a perfect correlation is a score of 1. That means a straight line, but its plus or minus sign determines what direction it goes. And the smaller the number, the less grouped, the less linear, the less clean that scatter looks like. Then we moved on to hypotheses. So we talked about the null hypothesis and the alternate hypothesis. The null hypothesis says nothing's going on. There's no relationship, no effect. Usually equivalence. This equals that. That's the null hypothesis, because in the boring world of nothing going on, everything equals everything else. The alternative hypothesis is usually the opposite of the null. something's going on. If we know the direction of that something, we say, well, this is actually bigger than this. If we don't know the direction, we say this is not equal to this. So that's how you write them, h sub naught and h sub a, or h sub 1. And from there, we looked at the errors, and we spent an entire class talking about the kinds of error that comes out of hypothesis generation. And this is critical for how we define our statistical significance cutoffs. We used the courtroom example of convicting an innocent man or letting a guilty man go free. So type 1 error is the idea that we incorrectly reject the null. Let me go back and remind you that we never say we accept the null. Some lazy statisticians will say, I accept the null hypothesis. I don't like that. We never accept an innocent person, you are incorrectly rejecting the null. You are saying something's going on when in fact something really isn't going on. In other words, the drug doesn't work, but we think it does. A type 2 error is failing to reject the null erroneously. So something actually is going on, but we didn't perceive it to be so. In other words, the drug actually works, or we didn't think it does, or a guilty person goes free. In society, we are very often more concerned about protecting the rights of an innocent person than we are about punishing a guilty one, in theory. So we tend to, much like in statistics, lean towards making sure we have small type 1 error, and the trade-off of that is we have a somewhat larger type 2 error. So get those concepts straight in your minds, the difference between type 1 and type 2, and the fact that we never accept the null, we only fail to reject it. Then we talked about directionality. So I mentioned that if you know that one thing is bigger than the other, then you state your alternative hypothesis as x is greater than 5. If you don't know that it's bigger, you just think it's different than 5, you say x does not equal 5. So if you know the direction, we do a one-tail test. If we don't know the direction, we do a two-tail test. And that tail refers to the opposing ends of the distribution, usually the normal distribution. Right. Then we moved on to the sampling distribution of the mean. That was a kind of a mind warping idea that I don't think I explained very well. The idea here is if I have a sample of kids and I'm testing their height, and I want to know is their average height equal to 5 feet, what I'm assuming there is somewhere a universe where all the kids have an average height of 5 feet. Wondering, is my sample extracted from that universe? So in other words, is the mean of my sample equivalent to the mean of all the samples of this theoretical soup of kids? So these sampling distributions are theoretical. They don't actually exist, but we try to estimate them. Okay, so we define our standard error of the mean as the standard deviation of this theoretical superpopulation, and we estimate. We say that it is the standard deviation of my population, of my sample, divided by the square root of my sample. And the reason for this particular formula, now there's a lot of reasons, but one reason you might want to think about is the standard error of the mean is going to be smaller than my standard deviation. How much smaller? Well, not that much smaller, but we estimate that the degree to which it is smaller can be modeled by 1 over root n. So think of it that way, if that helps. If not, just memorize the formula. Okay, we introduced the idea of confidence intervals. So a confidence interval is like a hypothesis test, but it's different in the sense that it just tells us the confidence by which we can express the measurement. So here is the confidence interval of a mean. And I've said it's a 95% confidence interval because I'm saying with 5% type 1 error, I'm 95% confident that this mean falls in this range. And I define it as plus or minus the t-value multiplied by my standard error of the mean. The t-value, I get that from a table. I look up 95% and my degrees of freedom. Okay, so then we moved on to lecture 10. In lecture 10, we talked about the standard error of the difference. And in these practice samples that I gave you, I realize a couple of students have thankfully pointed out to me that I made an error in those questions, and I warned you that I would because I did them fast. But the error was this: is I used an online calculator, and that online calculator used a different formula for the standard error of difference than I gave you. Don't worry about it. Use the formula that I gave you, and that's what will be reflected in the midterm. In the future, when you do this on your own, you're going to use computers anyway, and they're going to do the hard work and figuring out which is the appropriate variance formula to apply. So just as long as you understand the concept here. So the standard error of the difference is like the standard error of the mean, this theoretical superpopulation, but this superpopulation is populated by differences between groups. So this leads us to our t-test, which looks at the differences between groups. So somewhere out there in the multiverse, there's a universe where all the differences between groups are described a certain way. And we want to figure out, is the differences between our two groups taken from that theoretical universe? If that's too confusing, just memorize the formulas. So we introduce a t-test. The t-test is a test for comparing the mean of your sample to one of two things: an external value or another sample's mean. Okay. And we talked a little bit about p-values, and I want to remind you that if the p is low, the null must go. And how do we find lowness? Lowness is defined by if the p-value is less than or equal to our type 1 error cutoff, or alpha value. Usually, the type 1 error cutoff is 0.05. It isn't always, but often it is. Sometimes it's 0.01. People define it however they choose, but the standard is 0.05. Why? No reason. I put a paper up on your website if you want to read it about the historical origins of 0.05. It's long and arcane, but if you don't care about that, just memorize. If p is less than alpha, we reject the null. If it isn't, we fail to reject the null. So t-tests compare means. They don't compare medians or proportions or probabilities. Keep that in mind. We can only perform t-tests on data from that we can compute a mean. That means no nominal data, no ordinal data. Okay, only on interval and ratio data. Oh, my computer's moving slowly. Okay, so when can we do two tests? We're comparing the means of two samples, or when we're comparing the mean of one sample to a specific external value. Skip these two slides, not very useful. This will set the same thing over and over again. Okay, so you remember this slide. This summarizes the number of t-tests we have. We have the single sample t-test or the two sample t-test. Among the two sample t-tests, we can look at those that are dependent or those that are independent. And among the independent ones, we can look at those for which the variance is the same in the two samples or in which the variance is different from the two samples. In this class, by hand, we only did the single sample t-test and the dependent mean samples t-test. Right? Everything else we use computers for, but I want you to be aware of how they were done. So an example of a situation requiring a single sample t-test, well, that's comparing a mean to an external value. In other words, is the mean of your final exam 85%? That would be a single sample t-test. An example of a situation requiring an independent samples t-test would be comparing the means of two unrelated populations, like is the average height of the biology class equal to the average height of kids in the French class? So that's comparing the means of two unrelated samples. If I'm comparing the means of two dependent samples, that will be like, is your mean midterm mark different from your mean final mark? See, you guys are related to yourselves. Or is the mean IQ of husbands equal to or different than the mean IQ of wives? Those are dependent samples. Okay, so what are the two subtypes of independent samples t-tests? Well, equal variance or the same or different variances. How do we know which one to use? We do a certain test, Levene's F-test. Levene's F-test tells us, are the variances the same or different for the independent samples t-test? Okay, here's an example. A researcher wants to determine if plants grow faster using fertilizer 1 or fertilizer 2. In other words, are the heights of the plants different? in 2 fertilizer groups. So starting with seeds, he grows plants in identical conditions, and he randomly assigns fertilizer 1 to 7 plants and fertilizer 2 to 6 plants. What's the null hypothesis is going to be is the mean height of fertilizer 1 is equal to the mean height of fertilizer 2. That's the null. Nothing's going on. Okay, so we run the SPS output. Now look at the bottom box there. The bottom box shows us, can you see my cursor? I think so. Look at the cursor. So it says equal variances assumed and equal variances not assumed. And there are 2 p-values here. Okay, which one do we use? We use this one here, this p-value. This p-value tells us which one of these is true. So the null hypothesis for Levine's f-test is that the variances are the same. Here we have a p-value that's not low. The p-value is not low, the null does not go. So in other words, the variances are the same. So we use the top one, equal variances are assumed. And the top number says this. This is the p-value now for my t-test. Not this. This is the p-value for comparing variances. These are the p-values for the t-test. Which one do I use? It depends on that. We decided this is the one we use. In this case, it doesn't matter because these 2 p-values are pretty much the same. But this is how we look at this. Okay. So I just repeated what I just said. So now let's answer the question. Are the mean growth rates different between the 2 samples? A p-value of 0.269. That is not low. That is not lower than our alpha of 0.05. So the p is not low, the null does not go. Therefore, we assume that the null has not been rejected. In other words, the heights of the 2 groups are not different. Okay. Okay. Do we need to run Levine's f-test for dependent sample t-tests? The answer is no, because dependent sample t-tests are essentially running tests on the same groups or 2 really closely related groups. We assume that those 2 groups have the same variance. That's why we don't run Levine's f-test on dependent samples, because we assume already that the variances are the same. Here are the assumptions of doing a t-test: that the cases are randomly selected, that they come from a normal distribution, and the variances are more or less equal. Okay, how do we know if they are randomly selected? That's from how the study was designed. Is it a good study or a bad study? How do we know if they're from a normal distribution? Well, sometimes we don't. So sometimes we have to apply a certain kind of test, and that test is the Kolmogorov-Smirnov test. Okay, and much like our Levine's test, there's a p-value for that too. So the null hypothesis for the Kolmogorov-Smirnov test is that the data is distributed normally. That's the null. If the null goes, then it's not distributed normally. Here is the p-value for the Kolmogorov-Smirnov test that SPSS gives you. 0.2. Is 0.2 low or high? 0.2 is high. It's not lower than 0.05. So the null is not low. The p is not low, therefore the null does not go, and the data is distributed normally. We failed to reject the null. Okay. Can we skip the test of normality? Well, I didn't tell you this before, so don't worry about it for the midterm. But yeah, we can very often skip it. So if we have more than 40 cases per group, then that's usually a sign of probable normal distribution. And if the 2 groups are more or less the same size. What does more or less the same size mean? It means one group isn't more than 1.5 times the size of the other one. I didn't really talk about this in class much, so don't worry about that for the midterm, but now you know. So what if it's not normal? If it's not normally distributed, we can actually do another kind of test called the Mann-Whitley-U test, or Wilcoxon-Rank sum test. We won't be learning how to do these tests. I didn't tell you about this. It's not on the midterm, but now you know that this is the alternative in case you fail the normality test. Okay, so the independent samples t-test. We need f-test because we don't know if the variances of the samples are equal. We need to run the test for normality if the sample size are radically different. It's technically called Welch's t-test. Again, you don't need to know that for the exam, but there it is. Okay. Now the dependent t-test we spent some time doing because that was the one example we actually did together. But let me check my feed here. Still going on? Excellent. All right. So it's also called a paired sample t-test. We always assume the variances are the same. Essentially, you're running the same tests on the same people. We don't really test for normality on this one much, but probably should if sample size is small. And this is the classic students t-test, right? So we went through examples on how to do that, and you have some other examples on the website. So for significance testing, there are essentially three ways to do significance testing. We can either state the null, compute the t-test or whatever statistic we're computing, and then look up in our book the appropriate value. That's what you do on your exam because it's hard. That's what we did on the examples because it's hard, and it's a classical way of doing it. Or we can compute a p-value on SPSS and skip all that looking stuff up in the back of the book stuff, right? And then fail to reject the null or reject the null based solely on looking at the p-value. This is what most of us do in real life because we're lazy and we trust our programming. Okay? This is what we did back in the 30s and 40s. We made kids do hard work, and I'm making you do it now. This is what we do, really. And this is what we like to do. We construct a confidence interval for the difference between the means. And if the interval includes 0, then we assume there is no difference between the means. Okay. So other things to remember. For the t-tables. Oh, hang on. I got a question on someone's tweeted me something. Let me see here. Oh, no. Nothing related to this. Someone just retweeting me something clever I said earlier. I was hoping it'd be a question from somebody, but no. Okay. So for the t-tables, you need to know the degrees of freedom. So we compute the degrees of freedom in different ways, depending upon the test that you're doing. For a one sample t-test, it's the number of people in the sample minus 1. For a two sample t-test, if it's independent, it's the total number of all your peeps minus 2. And if the dependent test, it's the number of pairs minus 1. Okay. Then you need to know your alpha level. Usually it's 0.05. Sometimes it's 0.01. Sometimes it's different, but it's usually those two numbers. And you use those two bits of information to go to the back of your book and look up the appropriate t statistic. You'll need to know whether it's a one-tailed or a two-tailed. In this class, it's always two-tailed for t-test. So that solves your problem right there. Okay. And once you look up the value in the back of the book, you compare it to the number that you just computed. You take the absolute value. So if the table's value is bigger than your value, we fail to reject the null. If the table's value is less than or equal to your value, we reject the null. I don't tell you this, so you have to remember this for the exam. So speaking of the exam, what is on the exam? Dun, 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 dun. It's all multiple choice. I don't care about how you get an answer, assuming you're not cheating. So don't bother showing your work. Only the Scantron will be marked. So there are 70 questions in total, 69 real questions and 1 bonus question, right? If you get the bonus question, it's slapped on top of your mark. If you don't get the bonus question, it's not slapped on top of your mark. So 5 questions you could do math on, but you don't need to. You can just figure things out without computing anything, but you can do it the hard way and run through the numbers. 5 other questions you need to do actual computations on. So 2 of them are about probability. 2 of them are bivariate analyses. What does that mean? Those are things like odds ratios and relative risk and things like that. And 1 is a t-test. Dun, 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 dun. The rest are just theory. So if you're struggling doing the manual t-test, don't worry about it. It's only 1 question. On the computation, obviously they're going to be theoretical questions associated with t-tests you need to know. So the exam is very theory heavy. It's not computational heavy, as opposed to the final exam, which is probably computationally heavy. And the reason I do this is throughout the year, you have data assignments that give you plenty of practice and give me plenty of opportunity to evaluate your computational skills. On the exam, I want to know, do you understand the underlying assumptions and theory behind all of this? What will not be on the exam? I'm not going to ask you to calculate anything involving z-scores. I mean, sort of I do in the theoretical way, but nothing too intense. I'm not sure what that means. It sounds confusing, doesn't it? It sounds a bit misleading. So maybe you should study the z-scores anyway. I'm not asking you to calculate anything involving correlations. And I'm not asking you to calculate anything involving independent samples t-tests, because I didn't tell you how. And certainly no ANOVA, because we introduced ANOVA just last week, and we haven't had enough time to go through it all. So I give you the formula that I showed you earlier, the one sample t-test and the dependent sample t-test. I give the t-values, and I will bring some scrap paper. Otherwise, nothing. Okay, you can bring any type of calculator you want, even programmable, but I have trust in you that you're not going to violate the honor code of being in my class and programming with all kinds of stuff you should be programming, and bring some coffee and stuff for me. I've got some examples here, so let's run through some of them. In a t-test situation, confidence intervals are constructed around what? Anybody know? Obviously, you can't really tell me if you know unless you want to tweet me it. It's B, the difference between two means. Okay, good. That's what t-tests are looking at. In the following distribution, what's the mode? Let me see. The mode is going to be the most frequent number. Obviously, it's 15, so D. Which of the following is a continuous variable? Number of times married. Well, once, twice, 3 times. Can be married 1.5 times? No, that's probably ordinal. Age at first sexual experience. Car crash this past year. Can you have 1.5 crashes? No. Number of pages in a book. Can you have 4.5 pages in a book? No, you can't. So the answer is B, age of first sexual experience. Well, those are easy. Those are the kinds of theoretical questions I would ask. So that's all the slides. Hopefully that was useful to you. I apologize again for the sample questions, for getting the numbers wrong. As I said, I used an online calculator. But that shouldn't be too much of a big deal. Honestly, the midterm is pretty easy. I scared some people by telling you it's horribly difficult. It's not. The final's hard, but the midterm is pretty easy. So if there are no last-minute questions, I am going to sign off. Thank you very much, and I will see you tomorrow, bright and early, 11:30 a.m. in the classroom. Bye-bye. Stop sharing. Yay.